Welcome to Phenom AI, your place to learn AI. Today, we're diving into one of the biggest breakthroughs in modern AI, Mixture of Experts, or MOE. You know, this is the secret sauce that lets us build these enormous models with trillions of parameters, but without the insane costs and slowdowns you'd normally expect. So let's break down how it all works. So just imagine this for a second. What if you could build an AI with a massive, colossal brain, but for any given problem, it only had to fire up the exact parts it actually needed? Well, this whole idea is called conditional computation. Basically, the model's thought process changes depending on what you ask it. And that is the core idea behind Mo. And trust me, it is a total game changer for efficiency. All right, let's get into it. To really get why Mo is such a big deal, we've got to first talk about the problem it was designed to solve. And that problem is the brute force kind of clumsy way traditional AI models work. Yeah, these are what we call dense models. And think of it like this. To answer a super simple question, like, what's 2 plus 2? A dense model uses its entire brain. Every single parameter, every single connection gets fired up for every single word or token it processes. I mean, it's powerful for sure, but it is incredibly wasteful. And that wastefulness, it has a staggering cost. I mean, just look at this number. To train a dense model like Llama 2, it reportedly took 3.3 million NVIDIA A100 GPU hours. That's like running over 1,000 of the best GPUs out there nonstop for 134 days straight. The costs are just getting out of control. So this is really the whole story in one picture. On the left, you've got your dense models. All the parameters are firing all the time. Heavy, expensive. But on the right, you see the MOE approach, just some of the parameters, a fraction of the time. This is the big shift from brute force to, smart efficiency. Okay, so how do we actually get that efficiency? Well, this is where the big aha moment comes in. It's a really simple but powerful analogy that just makes everything click into place. Instead of one giant, overworked brain trying to do everything at once, what if you had a team of specialists? You've got your math expert, your coding expert, your language expert, and so on. So when a problem comes in, you don't bother the entire team. You just send it to the one specialist who really knows how to crack it. And in the world of AI, that specialist is called an expert. It's basically just a smaller, focused neural network that's part of the bigger model. What's cool is that they all start out identical, but as the model trains, they each learn to specialize in different kinds of information. One might get really good at code, another at poetry. Okay, but that brings up a good question, right? How does the model know which expert to send the job to? Well, for that, you need a really, really clever project manager. So let's see how that manager, the router, does its thing. Now, what's really fascinating is where this team of experts actually lives inside the AI. If you remember your standard transformer architecture, right after the self-attention part, every block has this thing called a feed-forward network, or FFN. The genius of Mo is that it doesn't reinvent the wheel. It just yanks out that dense, inefficient FFN block and swaps in this new, super efficient mixture of experts layer that you see here. Everything else about the transformer just stays the same. Simple, right? So that project manager we mentioned, its official name is the router, or sometimes the gating network. It's the small, fast little neural network that sits right at the front door of the Mo layer. Its one and only job is to look at every single token that comes in and make a split-second decision. Which one or two experts are the absolute best for this particular job? It's literally the traffic cop of the whole system. So let's walk through how that decision gets made, step by step. First, a token, think of it as a word, enters the layer. The router immediately looks at it and gives every single expert a score, like how good would you be at this? Then it just picks the experts with the highest scores, usually the top 2. That token is then sent only to those selected experts. They do their work, and finally, their individual answers are cleverly mixed together to get the final result for that layer. This whole process gives us 2 really important terms. The first is top K routing, which is just a fancy way of saying pick the K best experts. So like for Mixtral, K is 2. The second, and this is the most important one, is sparse activation. This is the secret to everything. Because we're only waking up, say, 2 experts out of 8, we're only using a tiny fraction of the model's total brain power for any single calculation. That's where all the savings come from. But, this does create a potential problem. What if the router gets lazy and just keeps sending all the work to the same 1 or 2 favorite experts? Well, that's a real challenge called load balancing, and it's super important to make sure all the experts are being used effectively. Okay, so that's the theory. It sounds great on paper, right? But what does this actually look like in the real world? Let's check out the results because this is where things get really, really impressive. So let's talk about Mixtral 8x7b. This thing is an absolute beast of an open source model from Mistral AI. And it has become the poster child for just how unbelievably powerful this whole mixture of experts idea can be. And this table just perfectly shows the MoE advantage. Take a look at the dense model, Llama 270B. It has 70 billion parameters, and for every single token, it has to use all 70 billion. Now look at Mixtral. Its total size is 47 billion parameters, but because of its smart MoE design, it only activates 13 billion for any given token. So it has this huge brain in storage, but when it's running, it has the cost and speed of a much, much smaller model. And this is exactly what Mistral AI themselves said about it. This technique lets them massively crank up the knowledge capacity of the model, its total parameters, while keeping the actual running costs and the speed or latency totally under control. It really is the best of both worlds. And here it is. This is the payoff. Even though Mixtral is using 5 times fewer active parameters than Llama 270B, it actually outperforms the much larger model on really important tests. I mean, look at these charts for math and code. Mixtral is just clearly ahead. It's literally doing more with less. So what's the end result of all this? Well, this lean, efficient design means Mixtral can run up to 6 times faster than a dense model like Llama 270B when it's actually being used. That is a massive speed up, and it's what makes these incredibly powerful models practical enough for people to actually use. So when you put it all together, what does this mean for the future of AI? Well, it seems to be pointing us in a very clear, very powerful new direction. So let's just quickly recap the big takeaways here. First, MoE lets us build massive models with way more knowledge, but for a fraction of the cost. This, of course, leads to much faster performance, both when you're training it and when you're using it. It also allows for this really cool expert specialization, where different parts of the model get really good at specific things. Now, it's not perfect. As we said, challenges are still there. That load balancing issue, making sure the router isn't lazy, is a tricky problem. It's often handled with something called an auxiliary loss, which is basically a penalty given during training to encourage the router to spread the work out evenly. And just keeping the whole thing stable during training is a hot area of research right now. And that leaves us with one final big thought. We now have a way to completely separate a model's raw knowledge from its running cost, giving us enormous power with incredible efficiency. So the question we really have to ask ourselves is this. Is this kind of smart, sparse, conditional computation the new gold standard for building the next generation of AI?